Hello, students. Today we're going to look at how rotation affects our mechanical energy calculations. So here, a bowling ball exits the return with an initial center of mass velocity of 2 meters per second. The ball rolls down an incline that is 1.5 meters tall. The ball rolls without slipping. How fast is the center of mass velocity after it rolls down the hill? So if an object rolls without slipping, then that's an important thing to consider. Now, we are looking at the center of mass velocity. So the center of mass of this ball is moving at 2 meters per second. Now, if I just consider this ball's rotating without moving, I can just imagine that we could take away the ground and just have the ball spinning here. As long as the ball does not slip, the tangential velocity at the edge of the sphere is going to match the center of mass velocity. And so I can treat this problem as both a translation problem, that is, the center of mass is moving, and at the same time, I can consider the rotation of the problem of the ball separately. So there are some other things to be concerned with, and that is, how does this affect my calculations? So let's look at this in a little bit more detail to see that really the addition of rotation does not change our approach to this energy conservation very much. So let's take a look. Now, initially, I have a center of mass motion, as I say, here. And the ball is going to roll down this little hill and end up down there. So as this ball is moving, I have the kinetic energy now comes into two forms. So kinetic energy now, when I look at kinetic energy, I need to consider two kinds of kinetic energy. I can look at the TKE. That's our good friend 1/2 mass times velocity squared. Now, that's translational kinetic energy, and I calculate that using the center of mass velocity. But now there's also rotational kinetic energy, or RKE. Now, that's going to be equal to 1/2 the moment of inertia times the angular velocity squared. So the translation, as this ball moves down the track, I have a velocity that causes it to translate, that is, to move in a linear fashion. That's the that causes what we normally would consider the kinetic energy. But I now also have to consider the energy found in the fact that the ball is rotating itself. So I have two types of kinetic energy. Now, potential energy is calculated using the center of mass position. And now, again, initially when people start doing these problems, they're a little confused. Like, why does the radius not affect this problem? Well, my radius r here, you would think that the height of the ball should be the height delta y plus the radius. But look at the bottom of the problem. When the problem reaches the end of the problem, the center of mass is still a radius above the floor. So where normally when we looked at a sliding object, we just looked at the hill, the height at the point of contact with the track, we still can do that because the radius of the object basically just shifts everything up the same distance. So my height is still going to be this 1.5 meters, and I can ignore the fact that I have a radius at all. It's not going to affect things. It's just shifting where I'm making my measurements. So with that, let's write our energy equations before and after, and see where we lead. Now, the other important fact about rolling without slipping is that means I'm not losing energy to friction. If I slip, that is, if the ball is turning faster than the friction can allow, I would lose heat as the ball slips against the floor until the ball slowed down enough to roll without friction. So we'll look at rolling with slipping another time. But for this, just be aware that if you do not have slipping, the problem is much simpler. So let's look at the initial location here. So my initial energy here, what form I have? Well, I have potential energy. That's going to be the mass of the ball times gravity times that height, delta y. I have translational energy due to the center of mass motion. That will be equal to 1/2 mass of the ball times the initial velocity squared. I also have rotational energy as the ball rotates. So that is going to be equal to 1/2 the moment of inertia of the ball times omega final squared. Now, if we consider what happens at the end, well, the energy at the end of the problem, I have now rolled down to the lowest portion, so there is no potential energy anymore. I will now have a new translational kinetic energy, 1/2 mv squared. Oh, should be over here. This is the initial angular speed, plus the final rotational kinetic energy, 1/2 I omega squared. All right, well, so basically the rotation energy just adds an extra term to my energy formulas, but I will still, as long as there's no energy lost to friction, set my energy at the beginning of the problem equal to my energy at the end of the problem. Now, this looks more like there are terms I don't know, especially the this angular velocity term and this moment of inertia. But a bowling ball is basically a solid sphere. So for a solid sphere rotating about its center, I know that I equals 2/5 mr squared. Now, if there is no slipping, then I can use my angular relationship that velocity equals r omega. That means that the initial velocity is going to be equal to r times the initial omega. So with that, I have a lot of substitutions I can do. So our initial energy is mg delta y plus 1/2 mv naught squared plus 1/2 I omega naught squared. That's going to be equal to one-half mv final squared plus 1/2 I omega final squared. Now, you can probably guess where this is going. We're going to use those relationships, substitute in, and a lot of variables are going to cancel out. So I have mass times gravity times delta y plus 1/2 mass, the initial velocity squared, plus 1/2, I'm going to substitute in for my I, that is 2/5 mr squared. I am also going to substitute in that omega naught equals v naught divided by r. Now, that needs to be squared. So what that becomes is v naught squared over r squared. On the other side, I have 1/2 mv squared plus 1/2, again, 2/5 mr squared times, again, making the same substitution. This is going to be the final velocity squared divided by r squared. And you can already see that there is a tremendous amount of cancellations about to happen. So first, I note that I have a mass in every single term. So the mass of the ball now cancels out. I also have an r squared over r squared in my rotational terms. So those r squared terms also cancels out. So bring it together now. I have g delta y plus v naught squared over 2 plus, well, here I have 1/2 times 2/5, so that's going to be 2 over 10 plus 2 over 10 v naught squared equals 1/2 the final velocity squared, plus again, I have 1/2 times 2/5 on this side, so that's 2 over 10 times the final velocity squared. So now it's a question of gathering my terms. So the g delta y is there. So I have 1/2 and 2/10. Now the common denominator here is going to be 10. So 1/2 is the same thing as 5 over 10. So I can replace this fraction with 5 over 10. 5 over 10 plus 2 over 10 is going to give me 7 over 10. So I have g delta y plus 7/10 v naught squared equals, again, same thing. I can replace this 1/2 with a 5 over 10, and then 5 and 2 make 7. So over here I also have 7/10 v squared. Now we're looking for this final velocity squared, so I can now just finish solving the math. So I'm going to multiply everything by 10 over 7. So over here I'm going to have 10g times delta y divided by 7 plus v naught squared equals v squared, or v equals square root 10g delta y over 7 plus v naught squared. Now if we go back up, we see that the initial velocity was 2 meters per second. And that the height was equal to 1.5 meters. And of course we're on Earth, so g equals 9.8 meters per second squared. So I get that the velocity v equals square root 10 times 9.8 times 1.5 divided by 7 plus 2 squared. And now some time for some calculator work. And I get the very nice answer that the final velocity would be 5 meters per second. So there you go. So it's the same procedure we did with other energy forms, but the rotational parts come into play. And as long as I have an equation for the moment of inertia, I can use my relationship with angular variables and my moment of inertia to get rid of a whole bunch of variables. You have to be super careful with the algebra, but if you are, it's not that bad. I hope this helps, and I will talk to you later.